the key objects were G torsors. S was something that, it was a set that was not empty with an action of G, which was simply transitive on the right. Okay? And they formed a category where a morphism between S and T, if there was any such a morphism, it would be a map, let's say phi, such that phi of SG is equal to phi of SG for every S in S, G in G. In particular, any such morphism is an isomorphism. So there might or there might not be morphisms depending on what kind of torsors I work with. I mean, I define torsors in the category of sets. So namely, this S here has only the structure of a set. And therefore, in that category for torsors, there's always such a morphism, because whenever you choose any element S here and any element T here, that determines a unique morphism. The morphism that sends S to T, and then you send every other element of the form GS, which covers uniquely each element of S, by this formula to an element in T. Right? So if I look at G torsors in the category of sets, any two G torsors are isomorphic. But the isomorphism is non-trivial, is non-canonical. It requires some choices. Okay? However, I could look at, the notion of G torsor as I defined makes sense in lots of categories. For example, I can look at a notion of G torsor, as I said last time, in the category of manifolds over a fixed manifold X. And then you'll get the notion essentially of what a principal bundle is, what a principal G bundle is. But let's just stick to sets with this category of morphisms, such that any two objects are isomorphic. Any morphism is an isomorphism. All right. And then what you'll notice first is that the set of isomorphisms, so if you give me the set of morphisms in this category of torsors, from S to T. So any morphism is an isomorphism. So this is a set of isomorphisms. And the question is it a G torsor or not? Does it have a natural action of G or not? Okay. For example, we've seen that if I put S is equal to T here, this set now becomes a group. It's the group of automorphisms of S by composition. And that guy is a G torsor, which is G by itself. Okay? But then this guy here has an action, because if you give me any morphism from S to T, okay, you can compose with the action later of G. Okay? So if you give me this phi, I can define a new isomorphism, phi G, which valuated at S, I could define it to be phi of S, and then acted upon by G, for example. Is it an action of G on the set of isomorphisms? So the first of all is it true that this phi G is... Vamos trocar para... Agora já não sei qual é a língua que corresponde. Fantástico. Ok, então... sorry. So the question is does this action of G on the set of isomorphism defined... Is it a G action? Is it a G torsor, what we get on this set? Well, first, we need to check whether or not that's an action. So I need to check that if I take two elements in G and I act by the product, so now this guy is a morphism. Well, first of all, we need to check whether or not it's well defined. Whether phi G is an isomorphism or not. So is phi G an element in this set? And then for that to be true, then I need that phi G acted upon on SH. So I'm just checking that definition. This should be equal to phi G of S acted upon by H. So now this side, by our definition there, is phi S acted later by G. No, sorry. This side here, by our definition of phi sub G acted on an element, is phi of that element, which is SH, and then later acted by G. And this guy here, by our definition of phi G, is phi of S, then later acted by G, and then later acted by H. So now T is a G torsor, so this is an action on the right. So this, by T being a G torsor, is phi of S acted upon by GH. And this side here, what can I say? So phi was a morphism, right? So since phi is a morphism, then we have again that rule over there that says that phi of an element and then acted by G is the same thing as phi of SH acted by G. And this guy now, since S is a torsor, this is phi of S acted upon by HG. Which again, since phi is a morphism, this is the same thing as phi acted on S, HG. And there's no hope that this is going to be true. So that formula there cannot be correct. So how do we correct it? So you're suggesting to put the G on this side. But if I put a G on this side, what does that mean? Right? So phi of S is an element in T. What does this mean?
Maybe inverse.
Sorry?
Oh, T inverse.
Good. So G does not act on the left. What I can try to do is to put some anti-involution of the group. Okay? But also, so I could try. Let's play this game, and we have time. And it's better just to try. So the first try is going to be in red. So the first try would be just to put a G inverse on this side, for example, which is something we did if I wanted to keep from torsors, so from actions on the left instead of in the right, and to get a representation, then I would have used a G inverse. But okay, so if I have that guy there, then where did we use that thing? Let's see again. So I want to check that this is equal to, well, this is phi of G applied to, so this is that equation there, right? So phi of G applied to SH. Here I took out an H, so I need that inverse. Is that right? No. No, that's just this equation. This is phi G applied to this element should be phi G S and H outside. So that's this equation, not this. That's what we want to check. So now, this guy here on this side was, by definition of phi G, is phi of S, and now there's this inverse that we just added there. But still this H is without an inverse. Okay? So now, again, by the fact that T is a torsor, this is G inverse H. Just associativity on the right. So this is T is a torsor. Now, here, this is the fact that phi was a morphism. So since phi is a morphism, it satisfies that equation. Therefore, I can put this g inside. But before that, we need to check this statement. So this equation here was that the definition of phi of g that says that is phi applied to this element, and then this g goes outside as an inverse. And now the fact that phi is a morphism would put this inverse inside. And now the fact that S is a torsor would put this associativity here. And now again the definition of the fact that phi is a morphism allows me to take this guy out. And I get the same order. So there's no hope. That's not a solution. So how do we solve this problem? Or we may not have a solution. We have two actions, and here we're only using an action in T. Right? So here I'm acting on phi's only using the action of G in T. But I could also use the action of G on S and hope for the best. So how does it go? Phi SG, and then a G inverse here, something like this.
That would be phi s. Because phi is in.
Correct, because phi is a morphism. So this would give me just this, which is let's just try one more. So let's just try. Let's probably this board. Right? So let's just try this definition. I'm just still going to use white. So the action of G on the side. Let's do the same thing as the original. It's just that with the action of S on S first. So if I define this guy to be phi of SG, then hopefully then we'll see later whether or not this needs to be on the left or on the right. Okay. So then, well, let's check again. So we want to check whether or not phi G is a morphism. Yeah. Then exactly, good. So this is the same thing as phi S acted upon by G, which is all we already checked that doesn't work. So putting it on the left or on the right doesn't work. So do we solve? How do we solve this? Or at least let's convince ourselves that we may not solve it. And we may not solve them. There's no reason for us to have this action. Because S has one action of G. T has one action of G on the right. The fact that I'm looking at morphisms commuting with that action kills that action. Why would I have another action? If I had two actions on one of these elements, let's say that T had an action on the left and on the right, and I look at things commuting with the action on the right here, then I would still have surviving an action on T on the left, which I could use to act on phi. But in principle, I don't see how Okay? All right, so, but let's keep this in mind for a second. Okay. What we do know, however, is that the set of morphisms from S to S is a group. The set of isomorphisms from S to S is a group, which is G. Okay? So we had proved this before, that the set of on this category from S to S is the group G, and this is with the composition. But then there's something we're doing wrong, because I have composition. So probably I would want to do this like this. So that's just the composition of morphisms. So if I was in a category, this would be the composition. And now I'm telling you that this guy here is G. And this is what I was hoping that this would be a torso. And this would go to the same thing. And the composition is associative. So if I look at a diagram where I put hum, just by abstract nonsense, so composition here, I could just take the identity here and compose these two. And this would go to hum as T, hum as S. Or I could use the composition here and the identity there to go to hum as T, hum as S. And here I could just use the composition to go to hum as T. And if you replace, whenever you see hum SS by G, that's the notion of being an action. That's the definition of being an action. So where did we do something wrong? I mean, either that board is wrong or this board is wrong. But if we're in a category, we expect to have that composition was the multiplication in G. Right? Under the isomorphism between hum SS and G, the composition is the multiplication in G. Hence,
that isomorphism is not natural. Right?
the isomorphism from SS into G? What do you mean? The identity, so we only need to check that this is a G torsor. So first we want to check that this is a G torsor. The second thing to look for is whether or not it has an element. And it has an element. The identity is an element. And remember that given any G torsor and any element, we identify the torsor with G, canonically. So perhaps we want to check this again. So why hum SS is a G torsor? But that's essentially equivalent to the problem that we originally had. Sorry? The more, so this group would be the identity? You're saying that this group here would be the identity. But that's not true, right? So we know that a morphism is determined, so choose any element. The way we did it last time was this. Choose any element S in S. Okay? Choose one. Fix it. So now, what are the morphisms from S to S? Any other element determines uniquely such a morphism. And any other element is uniquely determined by an element in G. So any other element is of the form G S. Yeah. SG. Right?
If you fix one morphism that send S to SG, then you want to check that it's a morphism. When you apply to SH, you should get SG.
Correctly, but the thing is that I get to choose the second element, and the choice of the second element determines a unique morphism, and that choice is equivalent to an element in G. So let's put it the other way around. Choose an element S in S. Okay? You get an isomorphism from G into HOM SS, which is given as follows. For an element G, you send it to the unique morphism that sends S to SG. This S is the one that is fixed. So let's put it to make precise. Put S0 here.
Yeah. I mean, the map send S0 to S0G maybe not a morphism. It is a morphism if and only if G is in the center, I think.
What? Wait. So let's check that. Let's determine that there is a morphism doing this, and there's a unique such a morphism. Okay, so how do I define this morphism? So I claim that there exists a morphism phi from S to S that does this, and there's a unique such a morphism. So how do we define phi? Well, any element S in S is uniquely of the form S naught times, let's use a different letter. Oh no, let's just keep it G for G in G. So I define phi of S. This should be phi of S naught times G, which if phi is a morphism, it has to be phi of S naught times G. And we are defining this phi of S. Oh, shoot. Yeah, so the letter is sort of like nasty. But okay, so probably I should have chosen here H, here H, here H, here H. And now here we get it to be S naught G H. Okay? And now S is S naught H, so yes. So that's an issue. So how do we correct that issue? We're getting closer to finding where the issue was. It's the same issue that we had there. Once we correct that issue, then it's going to be easy to. I'm confused. So you,
If you can define that by 5G, you can find that definition.
I'm a little bit confused. I don't understand what you want to do.
We want to see how if we can define that 5G.
Correct.
So assume that we can define it.
Okay, let's suppose that we can define it.
Then you compose 5 and 5G or the inverse of 5G.
Correct, and that's going to give me some element in hom SS.
Yeah, and you will have a formula as 5. That composition in S.
Which should correspond to an element in G.
Yeah, then you write it, then you
Well, but how, I mean, yeah, so I don't understand how,
yes, so you can know phi must equals to that. Because you know phi G inverse composed phi in element S should be S multiply H.
correct.
Then you compose phi G in both sides. You get phi S equals to phi G.
Yeah, but I guess it's going to be long to write that thing. I'm not sure if the formula is going to be very helpful. I think we're going to get to the same issue as here.
Yeah, I mean, then you can get that phi G is phi S multiply H inverse. Then, and we check that it's not going to happen. Can you write it?
No, I don't understand what you're saying. So you want to write the composition of the inverse, and you're claiming that you're going to get to this same formula here that we know it's wrong.
Yeah. With just one.
Go ahead.
I got here.
Yeah, sure.
If we define and this map is the from S to S.
Yeah,
It should be S multiply H.
correct. For some H, yeah.
So we know phi, we multiply phi G in both sides. We know phi S. And we change S, this as 0.
Wait, so what did you do there? So you did phi of on both sides,
Phi G.
phi g on both sides.
Yeah, we
Okay,
and we change the symbol.
sure.
That is very big. And this is
So you did phi of s, which is phi g of sh, which is correct. So you call that guy s0, which is phi of g of s0, which is phi of, that's correct. And now you use that phi isomorphism to write that guy there. Correct. So that's correct. And
we check that it's not happening.
wait, so there's this h there and the g on the other side.
But it has formula like that. Oh,
Yeah, and this h, and in principle, this h depends on s.
maybe you
So-
choose
So again, how do we solve that problem? Or was there a problem to start with?
Did we prove that isomorphism?
So last time I just gave you a bijection, but I didn't tell you how Which phi?
That phi you define, the one that takes S sub 0 to S sub 0 takes G.
No, well, so the thing is that there is, so the question is how to even define this map,
Yeah.
right? So what I said is, once you have two elements, once you fix one element in S, once I fix this, then what we get is an isomorphism between S and G as G torsors. And this isomorphism sends 1 here to S here. Right? And it sends, therefore, G to SG. And let's check that such an isomorphism exists, because it sends GH to, by definition, SGH, which is, since S is a G torsor, SGH. Okay, good. Right, so any element of S determines uniquely an isomorphism from G to S. Okay? So now I wonder, what are automorphisms on S? So I want to understand what are the set of automorphisms like this. Okay? But then again, if you give me such an element, so here's some S, and you give me such an element, so here's some T. There's going to be a unique isomorphism here that makes this diagram commute. Okay? Or put it in a different way, you can just make this one the identity. And this is the unique isomorphism that makes this diagram commute. And is it clear that there exists such an isomorphism? Okay, so that was the argument as to why a pair of elements
So you need a pair of elements to define.
Sure, but the thing is that this pair of elements defines you an isomorphism, but you might have two different pairs that give you the same automorphism. In fact, the pair ST gives you the same automorphism that the pair GS, SG, TG. So therefore, you just mod out by one of the action of G, and now it's just the choice of one element. And that was the isomorphism between, that was a bijection between G and the set of automorphisms of S. So then again, the question is now compositions. Oops. Come on, guys. It's not so hard. And I need to talk about functors in a second. That's the hard part. So perhaps the problem is that we're confusing two different actions of G. So we have a map from G to now in the category of sets. So I'll just write it like this. I'll write it as automorphisms in the category of sets from S to S. And here we need to be careful, because when we grab this element G, what is this automorphism? The only thing that we can look for is the action on the right. Right? And the action on the right would be the map that sends S to SG. So
I don't know if that map is even an automorphism of S. I'm not seeing how that map on the right is injected.
how this map is injective. Well, but that was the notion of being a torsor. The notion of being a torsor is that G has a simply transitive action on S. So for any element T, there's a unique G, and conversely, if you have an element that is stabilized, then G has to be the identity. That's the injection part. But the thing here is that composition here, well, I'm saying that this is a map. So let's check now whether or not it's a morphism of groups. Right? So a morphism of group would be that the map that corresponds. So let's call this map phi sub G. This is the action of G on the right. Right? So phi sub GH applied to S by definition is S and then GH. Now S is a torsor, so this is the same thing as SG and then H. And now this by definition is phi sub H applied to SG. And this by definition is phi sub H therefore applied to phi sub G applied to S. And now this is the composition in the category of sets of phi sub H composed with phi sub G of S. Okay? So therefore, this map here is not a map of groups. Because multiplication here does not go to the natural multiplication here, which is the composition. Okay? So even in the category of sets, I need to look at the opposite category. Whenever you have a category, so let's define that. Whenever you have C, a category, you have the opposite category, which are the same objects, but in this category, you define morphisms between X and Y in C opposite as morphisms between Y and X in C. So the composition now becomes with the opposite multiplication. And now, yes, in the category of sets with the opposite multiplication, then we see that this is a morphism. Okay, so that might help in our original problem.
I think that's just cheating. You just turn around the arrows.
That's fine, but the same thing is with putting an inverse. From G to G inverse is just a statement of, remember what I said last time. So a groupoid would, how was a groupoid a generalization of what a group was? A groupoid was a groupoid with one object was just a group. It's a category with only one object. So now the opposite of that category is G with the opposite multiplication. And G goes to G inverse is one way of taking the opposite multiplication, any anti-involution. So it's just as much cheating as putting a G inverse when we define representations. But okay, so I still want to solve this problem. Come on, guys. So I have this map from G to automorphisms of S as sets, which was this action on the right. So now the question is, do I have it to automorphisms in the category of G torsors? Well, let's see if an automorphism in the category of G torsors is by definition isomorphism of sets with an extra condition. Okay? So now we have this phi sub G that is defined to be this map. And I wonder if this map is a morphism from S to S in the category of G torsors. Okay? So for that, I would need to check whether or not phi sub g applied to S times H is equal to phi sub g applied to S and then acting on H on the side. Now this, by definition, is S, H, and then G. And this would be S, G, and then H. So this is not. So this map from G to the automorphism of sets does not give me an automorphism of G torsors.
When G is in the center,
Right, so if the group G, for example, is commutative, then there's no problem. But still, I'd like to solve this problem anyways. And the question is how to solve it. Okay, I'll continue this later. Let's let you think about this. Let me move on to perhaps to clarify a little bit what the solution to that problem would be. So remember that 2G torsors, last time, what I did is associated a functor from representations over a fixed field K to vector spaces over that same field. And so if you give me S a G torsor, then we've obtained such a functor, Fs, which sends the representation V to the vector space S, G, V. Okay? There's a bunch of functors that satisfies this. There's a bunch of properties that this functor satisfies. For example, Fs of the sum of two representations is naturally the sum of Fs of these vector spaces. So this is a sum in the category of G modules. And that's clear, right? Because this product here clearly commutes with sums. Also, well, I'll leave you this as a question perhaps. The category of representations of a group has a tensor product. And the category of vector spaces has a tensor product. So perhaps we can spend some time, but it's just as easy to see that it commutes with sums and it commutes with products. This tensor product has a unit. Remember that the trivial representation, K, was a unit for this tensor product. But also this functor Fs of the unit, so the unit is the field K, and as a representation being the trivial representation, namely all of G goes to 1, to the identity here. And Fs of that unit is S, let's check that, is S tensor G with the unit, which is just K. I claim that this is just the trivial vector space K. And that's clear, right? Because this here consisted on elements of the form S and a vector V, but this is equivalent to fix 1S. This is S naught. So here S is equal to S naught times G, and I can move the G to the other side. So every vector is just of the form S naught V, and V is an element in K. So therefore, Fs of 1 is just the unit for the tensor product in this side. The same thing for 0. Fs of the 0 representation is the 0 vector space. What else? That's about it. There are a bunch of functors that satisfy this property. So torsors were a category. I had morphisms of torsors. And vector spaces form a category. I have linear maps between vector spaces. Okay? So I'm going to build a category out of these functors. So let's define a category C, which will consist of functors from G modules to K vector spaces, and this is really the abstract part, that satisfy all of these conditions. Right? So they commute with sums, they commute with tensor products, they send the units to the units for both structures. And now I claim that this is a category. So how is this a category? Well, if you have one functor f and one functor g in this category, the morphisms between them are going to be natural transformations. And remember that natural transformations, what are these things? Well, this is, let's suppose that you have some phi here, then phi for a representation should be a map of a linear map in K vector spaces between f of v and g of v. So this is my phi sub v. And if you have a morphism of G modules from V to W, let's say sigma, then you obtain f of sigma here to f of W, G of W. Here you have phi of W, and here you have G of sigma. And this diagram should commute. However, I cannot take arbitrary natural transformations because my functors were not arbitrary functors. My functors were functors commuting with the natural structure on the category of G modules. Therefore, the natural transformations that I need to look for cannot be completely arbitrary. So these natural transformations should be compatible with star. So what I'm aiming for here is that the structure in the category of representations of a group determines somehow the group. So that's the kind of theorems that we want to look for. So in what sense the natural transformation should be compatible with star? Well, clearly that phi of v plus w should be the sum of v plus w. Namely, this guy should be a map from f v plus w into G v plus w. On the other hand, this guy, by the condition of this being compatible, this is f of v plus f of w. And this is G of v plus G of w. And I have a linear map between this and this, and a linear map between this and this. So I would require that this guy here should be hv plus hw, or phi v plus phi w. The same thing for the tensor product. So the phi of v tensor w should be phi of v tensor phi of w. So those are my morphisms. So I defined in this board a category of functors between representations on G and vector spaces. The only thing is, you give me a representation, I give you back a vector space with the property that tensor products go to tensor products and sums go to sums. One example of such a functor is a functor, I guess E would be in Portuguese for esquecimento. Let's call it F for forgetting. Okay? The functor, but I have this Fs. Well, it doesn't matter. Let's call the functor F for forgetting the functor that sends V to V. So this means I have a G module, and I just forget how G acts, and I just remember it as a vector space. Clearly, it preserves this structure. The sum of vector spaces goes to the same vector spaces, tensor product, that's it. So this functor is an object in the category C. So this guy here, which is the forgetful functor, is an object in my category C. In fact, what we have is a functor from, now we need a name for this functor, but okay, so we have a functor from the category of G torsors to the category C, which is the functor that sends S to Fs. And in particular, this functor sends, well, the torsor G to the functor, well, F sub G, which is the functor F. Is that clear? Because the functor that corresponds to the torsor G, right? What is Fg? Fg of a representation V, by definition, was G cross G with V, and I claim that this vector space is canonically isomorphic to V. In general, remember that in general, for any torsor S, if you give me any element S in S, you get canonically an isomorphism between S, G, V, and V. And the isomorphism is simply send the vector V to S, V. Okay? So in particular, the trivial torsor G goes to the forgetful functor. Claim. This is an equivalence of categories. Namely, any such functor comes uniquely from such a torsor. And that's an important statement. That just knowing how, from representations to vector spaces, preserving this structure, you recover the category of torsors. So if you do this geometrically, this is telling you that the assignment that for each representation of a group G, you get a vector bundle on a manifold, you recover uniquely what the principal bundle was. So for that, well, I would have liked for us to finish the first part, but let's at least get some insight as to what's going on. Okay? So the first thing to check is that this is indeed a functor. That this F, that from torsors to this category C is a functor. And that's kind of clear, right? So I need to check that if I have a morphism from S to T, then I get a morphism from Fs to Ft. This should be a morphism in the category C between these two functors. Okay, but then again, so if this morphism, I call this guy phi, then given such a morphism, I should give you, let's call this morphism, let's call it phi bar. Then what I need to give you is phi bar of V, which should be a map from Fsv to Ftv. But this is the same thing as Sgv, and this is the same thing as Tgv. And the map here, of course, is going to be the map phi times the identity over G. Okay? Okay, so that's clearly compatible with composition. So in fact, that map here is a functor from these two categories, from this category to this category C. So now, I would want to have the opposite. The opposite functor. Okay? So what I would want to have is, given a functor, how do I obtain a torsor? And my first guess, again, is going to be just like the first guess in the previous part of today's class. And most probably, therefore, we're going to have to solve it next time. So the first guess is just ask for torsors. Whenever you had a map, actually, I think we moved. whenever you give me two torsors, if there exists an isomorphism, if there is a morphism, then it's an isomorphism. Okay? And then again, as in the previous case, I would expect to have the set of these isomorphisms to be a G-torsor, because I can compose with the action of automorphisms from T to T, or from S to S. So, in particular, this set from the trivial torsor to any torsor, okay, the set of isomorphisms from G to S. What is the set of isomorphisms from G to S? Any such isomorphism gets determined by the image of one here that would go to such an S here. So the set of isomorphisms from G to S is naturally isomorphic to the torsor S. So that's a way of determining a torsor as a set of isomorphisms from G to S. So my torsor gets determined by the set of isomorphisms from G to my torsor. But that's a very good thing, because we do not know how this guy gives me a torsor. But what I do know is that if you give me two of them, I can look at the isomorphisms between them. In particular, I have one given object here, in as much as I had one given torsor in the category of torsors. In the category of torsors, I had the trivial torsor G. And in the category of functors, I have the forgetful functor F. So what I can look for is the set of morphisms between the trivial functor F and any other functor. Let G be an object in the category C. Then the set of morphisms between F and G. F is the forgetful functor. And this is a set now. And I claim that this set is a G-torsor. I'm using G for the letter G for two things. Here's a functor and there is a, yeah. So let's use a different name for functor. What's a functor? F prime. Is a G-torsor. Okay, so let's try to write down explicitly some actions that we might guess. Right? But it is what we would expect it to be. So I want to see what the category of G-torsor looks like in this category of functors. I know that the trivial torsor goes to the forgetful functor. And I would want, therefore, to have any other torsor is the same thing as maps from the trivial torsor to this torsor. Therefore, it should go to maps from the forgetful functor to my functor. So a posteriori, we know that this statement should be true. Okay? All right, so if I give you morphisms like this, I want this to be a G-torsor. Okay, so let's pick a phi here. And what I want to define is phi sub G, which should be an element here. In particular, I would want this to be, right? So what is an element here? For any representation V, I need to give you a map from FV, which is just this vector space V, and F prime of V. FV is the forgetful functor, so it's just V. Okay? But this should be a natural transformation. So namely, if you give me W, and you have a morphism here, here is phi G of V, here is phi G of W, here is sigma, and here is F prime of sigma. This diagram should commute. So this is what I want to define. And what I have is the morphism phi, which already is a map like this. It commutes like this. So probably we want to keep this. Well, no. Let's continue. Okay, so what's the only definition that we can think of? I'm given this map from V to F prime of V, and I want to produce another map from V to F prime of V, which is by the action of G. And of course, the only thing I can think of is to define phi acted upon by G applied to the vector V. Right? And here we see why the difference is between vector spaces and representation. It doesn't make any sense to look at phi V, right? So it doesn't make any sense to look at phi sub V. So here is sub V, and here's sub V of V, and then act on G there with G there. Why? Because this guy here would be an element on a vector space, not in the category of G modules. So I forget about the action of G modules, right? So it doesn't make any sense to act with G there. But V is a vector in this representation, in V. Therefore, I can act with G here. So I can define this to be phi V of the vector G acted upon, the V acted upon by G. So I can give that as a definition of this guy here. And now let's check if this is a well-defined object. Okay, so to check that this diagram commutes, what do we need to check? You give me a sigma, which is a map from V to W. Let's look at what this bottom part of this diagram is. This means phi acted upon by G sub W of sigma of V, which is, by our definition now, this is the same thing as phi W of G acting here. Now, on the other side, or the opposite side, this is the same thing as, well, phi, the last one is F prime of sigma applied to phi G V on the vectors V, which is the same thing as F prime of sigma applied to phi G sub V is the same thing as phi of G in V. Phi sub V. And for this diagram to commute, I need these two things to be equal. So what is this diagram giving me? Which is the data that phi was a morphism. So this diagram says that phi sub W of sigma of V is equal to, well, the top part, which is F prime sigma of phi sub V of V. Okay? So phi sub W of sigma of something is equal to F prime of sigma of phi sub V of something. So I would be fine if G commutes with sigma, which is fantastic because, and this is the important part, F of V is a vector space. But F was a very special functor. It was a forgetful functor. Right? And the sigmas that I'm allowing were in the category of, and this is important, these were functors from the category of G modules to the category of vector spaces. So the only sigmas that I allow here are sigmas that are morphisms of G modules. So the only sigmas that I allow are sigmas such that this thing here is equal to sigma of G of V. That's why my source category was not just arbitrary vector spaces, were just G modules. And the only morphisms that I allow are morphisms of G modules. So therefore now this is equal to this because of this diagram just applied to sigma of V. Okay? Okay, so we're in good shape. So this is a well-defined morphism. So now I need to check that this is an action on the right. Okay? So now I need to check that phi g h and this guy applied to V. Well, I need to check that this as a morphism is the same thing as phi g h. But this is the same thing as for every V, I need to check that phi g h V is equal to phi g h, and here's a V. Well, I guess here's a V. But then this is the same thing as checking that phi of g h V is equal to phi g h applied to V. But this is, and now I'm again in the same problem as the first part. Phi of g, well, here is correct, so this is GHV, and on that side, this is H acting on the side, so this is phi g acting on HV, and here is phi of GHV, which is good. The order, this time, it came out correctly. Okay, so I just proved that this set of morphisms is a set with an action of G on the right. So we're closer. So now I need to check that this is a torsor. So I need to have an action that is transitive and simply transitive. So let's check that the action is simple, at least. Namely, let's suppose that we have a morphism phi that is fixed by every element in G. And I want to check, oh, sorry. Let's suppose that we have an element in G that fixes all this set, so every morphism. So I want to check that that element in G is the identity. Okay? The action being transitive means two things. That if I have an element in G that fixes that set, then it's the identity, and then any two elements are connected by an element in G. That's a transitive condition. So the first one is that if I have an element in G such that phi g is equal to phi for every phi, then G is equal to the identity in G. So this is the first thing I want to check. Now, how can I possibly do that? So again, we need to use the category of representations of my group. Right? So clearly, if I look at, so this statement here is an equality inside of this set of morphisms from F to F prime. And this set of morphisms from F to F prime, I need to check it for every representation V. So this equal means that for every representation V in G modules, I need to look at an equality between phi G sub V and phi sub V. Now these are linear maps. Before these were natural transformations, now these are linear maps. And of course, this depends on V. If I take, for example, V to be the trivial representation, then there's no hope to prove such a thing. Because most probably, for V being the trivial representation, I will have this equality for every element in G. Okay? Because for the trivial representation, this guy here is K. F prime has to be K, because that was one of my conditions on my functors. It should send the trivial representation to the trivial representation. And certainly any G would make, any phi would satisfy that condition for every G. Okay? So this condition certainly would depend on my choice of representations for G. So what is the opposite of the trivial representation? Well, let's take a representation large enough such that G inside of this representation is faithful. So I think I didn't define it, so definition, V in G modules is said to be faithful if the morphism from G to GLV is injective. Namely, the only element that acts as the identity is the identity in G. Right? We know that for G being a finite group, there exist faithful representations, because the regular representation of a finite group is faithful. We've already checked that. So for G being finite, there exists a faithful representation. For G being not finite, then, well, it depends on the kind of groups that we're looking at. So now is the first time where I need finite groups. At no point before we needed finite groups. For semi-simple, for compact groups, these things still true, that there are faithful representations. But now we take a faithful representation for V, and I claim that this condition, I take V to be such a faithful representation. And now I look at this equation. And now that equation would mean that phi of GV is equal to phi of V for every V in V. And phi is invertible. Phi is invertible, why? Because any morphism in this category is an isomorphism. Therefore, this implies that G is the identity. So the action that I defined there is simple. So now we're missing the fact that it has to be transitive. Namely, given two morphisms phi and phi prime, I need to give you an element in G that sends one to the other one. So how do we do that one? So if you give me phi and phi prime, two morphisms from F to F prime, then there exists a unique G. Well, the uniqueness we just checked. So now we only need to prove that there exists a G such that phi G is equal to phi prime. So how do I construct that element in the group G? And this, we can look again as torsors. So somehow, if I look at torsors, this looks like having two different, on the torsor side, like this. Oops. I have an isomorphism like this, and I have an isomorphism like this. Right? And this determines, by taking the inverse of one and then the other one, it gives me an automorphism from S to S. And automorphisms from S to S were the group G. So that's the one way of getting an element in this. So, okay. So two elements phi and phi prime, two morphisms from F to F prime would give me such an element in G. Another way of doing this is the other way around. So instead of looking at these morphisms like this, I could have well used this. Just take the inverse of those guys. And now this composition of one inverse the other one is an automorphism between these two guys, which is just multiplication by G, by an element in G. Okay. So how do I do that now? Correct. So for every V, so I have this phi and phi prime, so I can do the same construction, explicitly the same construction. And if I look at phi prime inverse, so this is now a morphism from F prime to F prime. Okay? That's correct. And I can look at phi prime inverse phi, and this is now a morphism from F to F. Morphisms from F to F are very simple to understand because a morphism from F to F is, well, the same guy sub V. It's just simply a map from V to V. F of V is V as a vector space. Okay? All right, but now I want to know, I wanted to get an element in G, not an element from V to V. Why that morphism is coming from an element in G? So here's the deep part. I'm sorry? I'm sorry? Take?
You want to find the G.
I want to find a G.
Maybe take the NVI, the here
I'm a little bit confused.
I mean, just like regular representation.
Correct. We could look inside of the regular representation. So this, I could look at any vector space V. Certainly, if I look at the representation VV in the trivial representation, I'm not going to find anything. Right? And so this V has to be large enough such that G is inside of GL of V. So I'm going to be looking again at a faithful representation. But also I need to be careful because the statement is that this construction here, in principle, gives me back any linear morphism. But what I'm saying is that this linear morphism should be in the image of those morphisms that are in the representation of G. So inside of GLV, there are some morphisms that are very special. There are matrices that come from the fact that I'm representing a group G. And this is a strong statement. I'm saying that if I start with functors that are arbitrary functors, preserving tensor products and sums of representations, and you give me natural transformations that are arbitrary natural transformations, preserving these structures, then this composition here is not an arbitrary linear map, is a map coming from the representation of G. So why? Let's see how is it that this composition here is not completely arbitrary? Or how do I find that it comes from an element in the group G? Where does the group how does the group appear here at all? This is non-trivial. This is non-trivial. So I think I'll stop here and I'll do this next class. But then there's two questions. Let me just summarize what we did today. Okay? What I did is the following. On this we checked. First thing is to construct a category C, which is a category of functors. We checked that this was a category between representations of G and vector spaces. The next thing we did is to check that given any two objects in this category, well, I did it only for the trivial morphisms, but the same proof that I did there works for any two objects. Given any two objects, F and G in this category, then the set of morphisms is a G torsion. I did it for F being the forgetful functor, which is good enough. This we checked. And in order to find that this is an equivalent, oh no, I'm sorry. I didn't check that this is a G torsion. The fact that we're missing is the transitive part of the action. This we need to do next time. Right? It's this fact that here there's an element in G coming out. But we check that we have an action of G and that this action is simple. We have a functor from G torsors to this category C. And if I find this transitiveness, this would give me a functor this way. And the next step is to check that this composition is the identity or isomorphic to the identity on both compositions. Okay? But at the very beginning of this, on the side of G torsors, we failed already to do this. So on the side of G torsors, and this I'll leave to you for you to check, given S and T G torsors, morphisms from S to T, is this a G torsor or not? We failed to even construct this action here. But then again, what I did there is to construct it explicitly for F being the forgetful function. So perhaps you can try to look at morphisms from the trivial torsor into S being a G torsor, naturally. Which is clear because this morphisms is naturally isomorphic to S. So that's a G torsor. So the question is how to generalize from here to this picture, to arbitrary 2 torsors instead of just 1. Okay? So try to think about this for Tuesday. On Tuesday, I think I'll finish with this. So this becomes relevant if the category of torsors is not just sets. For finite groups, torsors are just, it's a kind of a trivial thing. I mean, this is a finite set, which is isomorphic to the group once you choose any element of this set. So it looks like a complete abstract nonsense. But if you define a torsor the same way I did, not just as a set with an action of G, just a manifold with a map to a fixed manifold X, with an action of G on the right, and the fact that being non-empty is just a local statement, so locally you have a section, that's the notion of a principal bundle. This functor here from principal bundle to the category of vector spaces, so these functors that go from representations of G to vector bundles now, is telling me that any such functor determines uniquely a principal bundle on a manifold. That's a deep statement.